Hello my dear students, I welcome you all in my YouTube channel Curious Physics, and today I am going to start the final topic and the final part of this particular chapter, alternating currents, and the name of the topic is transformers. Okay, till now we have covered the basic concepts of basically you can say the behavior of alternating current and alternating potentials when they pass through resistances, inductor and capacitor. Okay, then we have also studied the basic idea of root mean square values and also do some concepts of the phase relation between basically current and potential. Okay, so today's topic is transformer. So transformer is nothing but a basically electrical device which used to convert potential to another value. Okay, so basically if alternating current is passing through a transformer, or the alternating potential is passing through a transformer, it can basically transform its value. It can basically change its value. Okay, so the transformer is of two types. One is step up and other one is step down. In case of step up, the output voltage is greater than input voltage, and in case of step down, output voltage is less than input voltage. Okay, step up basically increase the potential and step down basically decrease the potential. Also, in case of step up, input current, or you can say output current, is less than input current, and in case of step down, output current is greater than input current. Are you able to understand my point or not? This is basically step up and step down transformers. Okay, and this is the basic you can say the basic construction of transformer. These particular two you can say two transformers can be made. In the first case the first case, two coils are overlapped with each other, and in second case, this is the structure, the basically primary coil and secondary coils are not overlapped. The basic principle is the basic principle is induction. Sorry, the basic principle is induction. Are you able to understand my point or not? Okay, this is the input, or you can say this is the input is provided through primary coil, and we will get the output through you can say secondary coil. Okay, now let's say the primary coil has the number of turns Np and the secondary coil has number of turns Ns. Okay, and when we supply the input alternating potential by the you can say through the primary coil, then there will be a flux change. In the secondary coil. There will be a flux change in secondary coil when alternating voltage is supplied through primary coil, the flux change take place in secondary coil. in secondary coil. Then according to Faraday's law, we know that induced EMF in secondary coil is nothing but minus ns into d phi by dt. Are you able to understand my point or not? Then if this particular EMF is induced in the secondary coil, then also there is also induced EMF in the primary coil due to also the flux change, because flux change also take place in primary coil, and in this case that particular flux is known as backward potential. That particular flux is known as backward potential. And same way EP or induced EMF in the primary coil, if NP is the term, d phi by dt. Are you able to understand my point or not? And in case of ideal conditions, for ideal conditions, induced EMF in secondary coil is equal to the, you can say, terminal potential in secondary coil, and induced EMF in primary coil is potential in, you can say the terminal potential in primary coil. Okay, now let's say this is equation 1 and this is equation 2. Then we can write ES upon EP is equal to NS upon NP, and ES and EP can be replaced by Vs by Vp is equal to Ns by Np. Are you able to understand my point or not? And potential in secondary coil can be written as Ns by Np into Vp. Vp is the input potential, you can say input potential or potential across primary coil. Are you able to understand my point or not? If Ns is greater than, if N, okay. also in ideal conditions, input power input is equal to power output if there is no loss. Then input power is nothing but IP, the basically current passing through the primary coil, into potential of primary coil is equal to current passing through secondary coil into the potential of, or you can say the terminal potential of secondary coil. Then Vs divided by Vp is equal to IP divided by Is, and which is equal to nothing but Ns divided by Np. This is basically the relation. If Ns is greater than the number of turns in secondary coil is greater than the number of turns in primary coil, you will get step up transformer, which will basically increase the potential. Okay, and we mean to say that Vs is greater than Vp, and you can say Is is less than Ip. If Ns is less than Np, then the transformer will be stepped down. In this case, Vs is less than Vp and Ip is less than Is. Are you able to understand my point or not? Basically the final potential and final current as compared to input values depends upon the ratio of Ns and Np, the number of turns in secondary coil and number of turns in primary coil. Okay, are you able to understand my point or not? And in this type of transformer, the basic assumptions you can say for ideal conditions. The basic assumptions to get these values, or you can say to get this particular type of derivation. The first is input resistance and input current is small. Input resistance and input current is small, same as for basically output current and output potential is small okay. Not output potential, basically you can say not output potential, you can say output resistance is small, and there will be no flux leakage, this is the basic conditions, this is the basic assumptions, okay, for ideal transformer. Ideal transformer, are you able to understand my point or not? Basically the main in output is output current should be small, output resistance may be or may not be small, okay, but these are the ideal conditions, are you able to understand my point or not? This is basically a device used to change the potential, okay. Next is, what are the issues or basic problems in the transformers? The first one is leakage of flux. Flux mean to say that input flux is not always equal to the output flux, okay. And the solution is, this particular issue can be resolved by, you can say overlapping the coils, overlapping the coils, mean to say that to basically reduce the area through which the flux cannot be leaked, okay. Overlap the coils. Second is nothing but, the second main issue is resistance of the coils, which basically alternate the value of currents or the change the value of currents. So the resistance of the coil can be reduced by making thick coils, okay, thick coils. And why? Because the resistance, you know that resistance is nothing but resistivity into length by area. If we make thick coils, means area will increase, and if area will increase, the resistance will decrease, okay. Third main point is eddy currents. Eddy currents are nothing but the circular currents which are produced in you can say the soft iron, due to change in magnetic flux, magnetic flux. So these eddy currents can be reduced by laminating the core. And I think I have forgot to tell, in this particular primary and in secondary coil, there is a soft iron core. The soft iron core basically increase the net magnetic field, increase the value of net magnetic field, which we have studied in chapter, I think, 4, the magnetism in matter. If you introduced a particular magnetized, or you can say the material which have high magnetic susceptibility in a solenoid coil, which will basically increase the net magnetic field indirectly, which will increase the net magnetic flux, because we know that the magnetic flux is nothing but BA cos phi. Fourth point, by laminating. Fourth basic point is magnetization of materials. Magnetization of materials. The technical term for this is hysteresis loop. Hysteresis loss, which magnetization of materials, because there is a change in magnetic field, which will basically magnetize the material, okay. So, and this will indirectly increase the heat, which will indirectly increase the heat loss, Okay, same as the eddy currents. If there is a current in soft iron core, that will also lead to the increase in heat. So that's why hysteresis loss basically can be reduced by use less magnetized material. Use less magnetized material. This is a short topic, not a very big topic, very small topic, so you have to focus on just the theory portion, not to deep dive in this particular topic for your board exams. Okay, are you able to understand my point or not? So this is basically the basic concepts of transformers, and these particular concepts you can say depends on the values of number of turns in secondary and primary coil. What is the meaning of step up and step down, and what is the basic condition of currents and potential in case of step up and step down. Okay, so this is the basic idea, and this is all about this particular chapter, transformers. Okay, are you able to understand my point or not? Okay, next is the examples, or you can say the exercise part. In exercise part, the question number 1, a 100 ohm resistor is connected to a 220 volt 50 hertz AC supply. What is the RMS value of current? And IRMS is nothing but VRMS divided by R, and here VRMS is 220 and R is 100. You will get the value. What is the RMS value of current? What is the net power consumed over a full cycle? What will be the power? And the power in case of resistive circuit, we know that IRMS into VRMS. Okay, so this is the answer of first question. Okay, always remember the power consumption is take place along the resistance, and the value is IRMS into VRMS. Are you able to understand my point or not? Next is the peak voltage of an AC supply is 300 volt. What is the RMS value? If the peak volt, your VM is 300 volt, then the VRMS is nothing but 300 divided by root 2. You will get your answer. Second is the RMS value of current in AC circuit is, and the second part of 7.2 is the RMS value is IRMS is 10 ampere. What is the peak value? Then I peak will be nothing but 10 into root 2 or 10 into 1.41. 10 into 1.41. Are you able to understand the basic idea? Just directly formula based questions. Okay, next is 44 microhenry inductor is connected to 220 volt 50 hertz AC supply. Determine the RMS value of current in the circuit. Okay, so in case of inductor, the inductive reactance is XL, can be written as omega into L. Omega is 2 pi into frequency into inductance. 44 into 10 raised to power minus 3. You will get XL. And for IRMS, you will get 220 by this XL. You will get your value. Are you able to understand my point or not? 7.4 a 60 microfarad capacitor is connected to this. Determine the RMS value of current. In case of capacitor, the capacitive reactance is 1 omega C, and that will be 1 by 2 pi frequency into capacity. 60 into 10 raised to power minus 6. You will get this particular capacitive reactance, and IRMS will be you can say 110 the potential VRMS divided by XC. You will get your answer. Okay, these are basically directly formula based question. Okay, so these are not basically you can say the not a very conceptual type of questions. Okay, are you able to getting my point or not? Next is in exercise 7.3, what is the net power absorbed by each circuit over a complete cycle? And we know that in case of inductive and in case of pure capacitive circuits, if there is no resistance, the net power loss is 0. Okay, are you able to understand my point or not? 7.6, a charged 30 microfarad capacitor is connected to a 27 microhenry inductor. What is the angular frequency of free oscillations? Free oscillations means the frequency of resonance, resonance, and the frequency of resonance will be nothing but 1 by 2 pi into under root L into C. The value of L is inductor and value of C is capacitor. You have to directly put that values and you will get your answer. Okay, are you able to understand this particular question? These are directly formula based questions, nothing so special about these questions. Next is 7.7. A series LCR circuit with R, L and C is connected to a variable frequency when the frequency of the supply equals to the natural frequency of the circuit. What is the average power transfer to the circuit in one complete cycle? In case of particular this case, sorry, the natural frequency will be nothing but 1 by 2 pi under root LC. Okay, are you able to understand point? You will get the value of resonance, you will get the value of that particular natural frequency, and what is the average power transfer to the circuit. In case of resonance omega c, in case of resonance XC is equal to XL, means there will the net impedance is equal to the value of resistance. So impedance will come out to be R, and here R is nothing but 20 ohm. Okay, are you able to understand my point or not? And here, so you will easily get the value of current, and the current will nothing but 200 divided by R, and you can say the power is nothing but V into I. You will easily get the power. But here the basic concept is at this frequency XC is equal to XL, and in impedance, if there is XC is equal to XL, and you know that the net resistance offered by in case of resonance will be equal to value of resistance, because the impedance is nothing but by formula you know that R square plus XC minus XL square. If XC is equal to XL, the net impedance will come out to be R. Just we have discussed this particular point. Are you able to getting my point or not? This is not a very tough question. This is basically easy directly formula based question, but you have this particular concept should be in your mind. When there is a condition of resonance or free oscillations, then there will be XC is equal to XL, mean to say that the total resistance is offered only by the resistance. There is no role of XC and XL. Okay, question number 7.8 shows a series LCR circuit connected to a variable frequency L, C and R. Okay, then you have to find the frequency which drive the circuit in resonance. So A part directly formula will be 1 by 2 pi into under root L into C. Second part, obtain the impedance of the circuit and the amplitude of the current at the resonating frequency. In case of same as the question number 7.7, at resonating frequency the impedance is nothing but the resistance, the value of resistance, and the answer will be directly 40 ohm, because at resonance XC is equal to XL. And the third point, you have determined the RMS potential drop across the three elements of the circuit, so that the potential drop across the LC combination is 0. And at the resonating frequency, yes, at resonating frequency as resonating basically that first of all you have to find the value of current. We have to find the value of current, and the current will nothing but V by R, because impedance is equal to R. In case of, okay, let's say here the value of current will be nothing but V by Z, and here at resonating frequency V by R, because XL is equal to XC, then the potential across R will equal to potential across R, I into R, and potential across C is equal to I into XC, and potential across L is I into XL. But these both are in opposite signs, because we have seen in phase diagrams phase diagrams, these are equals at resonating frequency, and that will cut each other, because we know that you have remembered this phase diagram, this particular phase diagram. This is VC, this is VL, and this is basically V and I along R. Okay, so this is the basic ideas about this exercise of this particular chapter, alternating currents. Okay, so okay, that's all from my side. So basically keep practicing and try to solve all the questions by yourself. And thank you so much. Take care. Have a nice time. Namaskar. Bye bye.